Ancient stars shed light on Earth's similarities to other planets. New method used to study planets. Geochemistry implies that Earth is not unique. It is unique. It is unique, you turds. Look. The process that creates Earth maybe not unique, but Earth is definitely unique. That's like saying I'm not unique. Of course I'm unique. But are there other people like me? Yes, of course. So where they are going with that terminology, I have no idea. And for those that are new to the series, stars become giant rocks. Giant differentiated rocks. Check this out. There's a white dwarf that expands greatly to blue giant, and then the blue giant starts dissipating its heat, mass, and energy, and eventually becomes a red or yellow dwarf, orange dwarf, red dwarf, brown dwarf, and then a Jupiter, and gray dwarfs, Neptunes, all the way down the line. Until eventually left over, you have a giant rock that has life on it, given it's evolved on slow enough timescales. The stars we see in the night sky, all hundreds of billions of them, well, not us, for instance, I can't see hundreds of billions of stars. I mean, I technically can if I look at a galaxy and I see the Andromeda galaxy with a pair of binoculars. I know there's over 200 billion planets there, which that's what a star is. It's a young planet. I don't know. I'll read this out to you. Go ahead and have a little story time here, and I'll break it down as I see it. Earth-like planets may be common in the universe. A new UCLA study implies. Well, obviously they're common because the process that creates them is in-your-face common. Those are young planets. That's what stars are, young planets. We can see hundreds of billions of them. I just said that. A team of astrophysicists and geochemists present new evidence that the Earth is not unique. The study was published in the journal Science on October 18th of this year. Quote, "We have just raised the possibility that many rocky planets are like the Earth, and there's a very large number of rocky planets in the universe," end quote, said co-author Edward Young, UCLA professor of geochemistry and cosmochemistry. Well, Mr. Young, that's pretty obvious if you were to know what stellar metamorphosis is. That's literally what I've been saying for the past 8 years. They're so freakishly common that there's so much life out there that if you were to fully comprehend it, I'm pretty sure your brain would explode. It would explode. You wouldn't be able to function in life if you knew how much life is actually out there. You would just be like, whoa, what is all this? Like, Earth is nothing. Earth is just a tiny speck. There are freaking trillions of specks just like us running around there right now. Yet, don't tell them that. The scientists led by Alexandra Doyle, a UCLA graduate student of geochemistry and astrochemistry, developed a new method to analyze in detail the geochemistry of planets outside of our solar system. Doyle did so by analyzing the elements in rocks from asteroids or rocky planet fragments that orbited 6 white dwarf stars. To Alexandra Doyle, you can analyze the elements of young planets. They're called stars. That's what spectroscopy is. You're studying the geochemistry of the planets, the young planets. Yet all your colleagues are calling them stars in their head. They're separating, they're differentiating the two. There's no difference. See, that's the problem you guys are having. We're studying geochemistry and rocks from other stars, which is almost unheard of. No, it is not almost unheard of. Young stars, young planets are bright and shining. It's spectroscopy. We've been doing it since the late 1800s. Quote, "Learning the composition of planets outside of our solar system is very difficult." Again, this is from another person, said co-author Hilke Schlingting. I can't pronounce this name. Looks German. UCLA Associate Professor of Astrophysics and Planetary Science. Quote, "We used the only method possible, a method we pioneered, to determine the geochemistry of rocks outside of the solar system. Spectroscopy. That's it. It's been around for over 100 years. White dwarf stars are dense, burned out remains of normal stars. No, white dwarfs are not dense, burned out remains of normal stars. A white dwarf is a very young baby seed star. White dwarfs belong at the very beginning of stellar evolution, and then they expand outwards. The burned out remains of ancient stars are what you guys are calling planets. You have it backwards. Their strong gravitational pull causes heavy elements like carbon, oxygen, and nitrogen to sink rapidly into their interiors, where the heavy elements cannot be detected by telescopes. The closest white dwarf star Doyle studied is about 200 light years from Earth, and the farthest is 665 light years away. Quote, by observing these white dwarfs and the elements present in their atmosphere, we are observing the elements that are in the body that orbited the white dwarf. Again, it's very unlikely that that's true. A white dwarf is a very young star, yes, but just because a body's orbiting it now doesn't mean it was always like that, and also doesn't mean that, because, okay, to them, they look at white dwarfs as being the end stages of stellar evolution. So naturally, if a white dwarf's there and there's a body orbiting it, then that body that is orbiting it is very, 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 very old as well, which means the white dwarf was absorbing a lot of material from that body that was orbiting it for billions of years. But what I'm saying is, the white dwarf is actually very, 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 very young. It's a baby seed star. It hasn't even gone through the majority of its evolutionary sequences yet. It's too young. So when these people are looking at the white dwarf saying, oh, well, what you're studying is material that's entered into it early in its history, they're full of it. They're full of it. They're just making that up because they want to agree with the models that they've already preset as being the truth. TM, the truth. And that being said, they're completely misguided. And what I'm also what the listeners should also realize here is a lot of times, I'll go into that. I'll go into one of the main ideas here is that these astrophysicists, they're reaching some correct conclusions sometimes, but based off of false premises that don't really lead to the conclusion. I'll go over that a little bit later, and I read this whole article already. But anyways, here we'll go step by step again. By observing these white dwarfs and the elements present in their atmosphere, we are observing the elements that are in the body that orbited the white dwarf. I remember that. Doyle said, the white dwarf's large gravitational pull shreds the asteroid or planet fragment that is orbiting it, and the material falls into the white dwarf, she said. Quote, observing a white dwarf is like doing an autopsy on the contents of what it has gobbled in its solar system. Sure. Maybe. But it's too young. The material that it formed out of was already there. It never actually, the material is what it formed out of is in its atmosphere. But that isn't to say it had been absorbing everything else for billions of years, because it's too young to have been doing that. The data Doyle analyzed were collected by telescopes, mostly from the W.N. Keck Observatory in Hawaii, that space scientists had previously collected for other scientific purposes. So they took leftover data and they made something out of it, and I admire that. That's really good. I like that idea. When you have data that nobody wants, and then you can make sense of it, kind of like what I'm doing. I'm using data and history of science that nobody wants, and I'm making sense of it and making it something really special. I admire that approach. Quote, if I were to just look at a white dwarf star, I would expect to see hydrogen and helium, Doyle said, but in these data I'll also see other materials such as silicon, magnesium, carbon, oxygen, material that accreted onto the white dwarfs from bodies that were orbiting them. That's the assumption. They're saying that the material was accreted from bodies that were orbiting it. They don't know that for sure. They're seeing something and then they're interpreting it in the light. This is where the interpretation takes place. They don't know if those bodies had been orbiting it. They don't know the fact that, from my perspective, the white dwarf formed from that material from the very beginning. And it's always remained in there. So there's that. When iron is oxidized, it shares its electrons with oxygen, forming a chemical bond between them, Young said. This is called oxidation, and you see it when metal turns to rust. Oxygen steals electrons from iron, producing iron oxide rather than iron metal. We measured the amount of iron that got oxidized in these rocks that hit the white dwarf. We studied how much the metal rusts. The rocks from the Earth, Mars, and elsewhere in our solar system are similar in their chemical composition and contain a surprisingly high level of oxidized iron, Young said. We measured the amount of iron that got oxidized in these rocks that hit the white dwarf, he said. The sun is mostly made of hydrogen, which does the opposite of oxidizing. Hydrogen adds electrons. The researchers said the oxidation of a rocky planet has a significant effect on its atmosphere, its core, and the kinds of rocks it makes on its surface. Quote, all the chemistry that happens on the surface of the Earth can ultimately be traced back to the oxidation state of the planet. That's correct. But what they don't realize is the oxidation state of the planet wasn't a state in which the Earth was always the size it is right now, with the same exact amount of isotopic abundances, such as there's this set of oxygen here, this set of nitrogen here, this set of carbon here. If you try to model what the Earth is now and then reverse engineer the Earth as having different oxidation states on its surface, given the mass didn't change at all, what you're going to end up doing is skewing reality, because you're going to be making a lot of materials that are in the interior of the Earth come up, and you're not going to be able to make things happen the way you imagined it. Unless, what I'm saying is, if you can have the oxidation states and the material be a lot different than what we're familiar with. And that's the whole purpose of this theory. The oxidation states of the inner atmosphere were a lot different when the Earth was a lot younger. It had a shitload more hydrogen in it. And when I mean a shitload, the majority of the Earth was hydrogen and helium when it was very young. So naturally, if a scientist can actually look at the young stars as being early Earths, they can then draw models up to actually determine the oxidation states of the interior as the star was evolving. So you can give not only a more, but a completely developed understanding of how Earth was in its past if you actually look at the young Earths that were much more gaseous and even shined like the sun. But let's go ahead and continue here. All the chemistry that happens on the surface of the Earth can ultimately be traced back to the oxidation state of the planet. Yes, but it isn't just a single oxidation state. And that's what I want to stress. It's multiple different levels of oxidation states and temperatures and pressures and masses. The entire star itself was extremely different. What we see on Earth now, this is technically an alien world that we're experiencing versus what Earth was in its past, when Earth was in its more energetic state before it even had life on it. So we have to keep that in mind. Earth as it is now is alien to the earliest stages of Earth's history. Or if you want to look at it in reverse, this is the normal part of Earth that we're experiencing, and Earth was much more alien in its past. Very, 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 very different in every single way, except for the fact that it was round. That's the only real property that it kept when it was very young, is the fact that it was round. Everything else was different. The fact that we have oceans and all the ingredients necessary for life can be traced back to the planet being oxidized as it is. The rocks control the chemistry. Wrong. The rocks do not control the chemistry. You have to first form the rocks to begin with, and they never talk about that. The geochemists, they assume Earth has always been made of rocky material. Well, how'd you get the freaking rocks to begin with? Okay? What happens is they're looking at Earth as it is, okay? To form the rocks to begin with, there had to be extreme temperatures and pressures in the interior of a gas giant star. And that's where the majority of the rock formation happens. So, yeah, it's basically that simple. They're kind of closing their mind off, saying, we have to explain everything with Earth, what's on the Earth now, inside this little itty bitty box. It's like this. Everything has to fit in here. And the observations we have of exoplanets being much more massive and very, very different. Oh, that's the exoplanets. We don't have to worry about that. No, those are the young Earths. And it's a continuous spectrum from very, very, very early stages of evolution. So the rocks controlling the chemistry, no. It's the star itself that controls its own chemistry. The rocks are just a byproduct of very, very, very early chemical reactions and under different temperatures and pressures, very early in the Earth's history. And it says here, until now, scientists have not known in any detail whether the chemistry of rocky exoplanets is similar to or very different from that of the Earth. No, you have known. I've known since 2011. A lot of these objects are exactly like Earth because the process of stellar evolution is ubiquitous. The stars make the rocky worlds, and in the same proportions, given they evolve on slow enough timescales. And if they evolve too fast, then the proportions of the rocks will change, and that also signals that it will either form life or it won't. That's why this is an earlier graph, but the rate at which it evolves in a slow rate would be up here, and a fast rate would be down here. And sometimes maybe a star will evolve way too fast, and will fall below the threshold for forming life and the rocks that we're familiar with on the ground. So it won't even have crystalline structure that's made of silicon and oxygen. Maybe it will be mostly oxygen and iron crystalline structure, more felsic materials. No, mafic materials. Mafic is iron rich, felsic is iron poor. I got that backwards. And it says, how similar are the rocks? The UCLA team analyzed 2 rocks from the Earth and Mars. And Doyle said, very similar. They are Earth-like and Mars-like in terms of oxidized iron. We're finding that rocks are rocks everywhere with very similar geophysics and geochemistry. And the reason why they're similar everywhere is because that's the ubiquitous process. The process that makes stars evolve, and the chemistry that's inside the star is going to change on a set basis. It's basic stellar evolution. It's not like, the process of planet formation is unique over here. The process of planet formation is unique over here. The process of planet formation is unique over here. No, it's a single process of stellar evolution. And we're looking at various stages of this process when we observe the stars and the exoplanets. The exoplanets, that's what the stars are. But I don't know. Let's see if it gets through their thick skulls, so to speak. But I'm trying to be nice when I talk about this stuff. It's always been a mystery why the rocks in our solar system are so oxidized. No, it has not always been a mystery. These people, they live in a bubble. I've known this since 2011. The reason why the material is so oxidized is because when a star is young, it has lots of oxygen to do the oxidation. The third most abundant element in the sun in young stars is oxygen. It goes hydrogen, helium, and oxygen. Well, naturally, why do we have oceans? Why are there ocean worlds? It's because the oxygen combines with the hydrogen when the star evolves, and it just stays put. That's why there's water. It's that simple, people. This isn't difficult to understand at all. Okay, but basically, that's basically it. The research was funded by NASA. Everybody's working together. We're all singing Kumbaya. Yada, yada, yada. I made this video long enough. I'll link this paper to the bottom of the page. There you go.